So I'm Prajkta Mane. I'm a postdoctoral fellow at Lunar and Planetary Institute and NASA Johnson Space Center. And today I'm going to talk about meteorites. But let's talk about today's date, the asteroid day first. It is actually the anniversary of a very special event called Tunguska event. This happened on 30th June in 1908 when there was a meteorite fall in Tunguska region in Russia. However, no rocks were actually recovered from this. But there is this huge scar in this forest that was preserved, suggesting that there was a meteorite impact. And 30th June is the anniversary of that impact, and that's why it is celebrated as the Asteroid Day. All right, so what are meteorites actually, and what materials do they come from? So there are three different types of meteorites: carbonaceous chondrites, or the chondritic meteorites, which are basically aggregation of different particles that form in the early solar nebula, and they just accrete together, forming these stony meteorites. They are very similar. Their spectra actually match with the type C asteroids in the asteroidal belt. Some of these rocks, when they grow large enough and they have enough radioactive heat, they will undergo melting and differentiate into layers, just like how our Earth is differentiated. It will have all the heavy elements like iron and nickel, they sink to the core, and all the lighter elements that are made up of mostly silicates and other things, they remain in the mantle and the crust. So the meteorites that these meteorites, luckily for us, collide with each other, fragment into pieces, and then they're brought to Earth so that we can study or analyze the course of these ancient planets or planetesimals. So these meteorites that are rich in iron and nickel are called iron meteorites. You also have achondritic or the stony meteorites, where most of the material that stays in the mantle, which is lighter and is made up of silicate material, forms these achondritic stony meteorites. So for stony meteorites, you have chondritic stony and achondritic stony. The other metallic meteorite is iron meteorite. There is a combination of both though. Somewhere between the core and the mantle boundary, the core is made of metal and the mantle is made of silicate. Somewhere in between them, you will find the mixture of both materials. So that's where these very special meteorites called pallasites come from. They're very pretty to look at. All the shiny material that you see here is iron and nickel metal, whereas all the greenish material is a silicate. It's a very special silicate mineral called olivine, which is also actually very common on terrestrial rocks. All right, so where do meteorites come from? The major source of meteorites that we study in the lab comes from the asteroidal belt, where there are a bunch of asteroids. There are some meteorites, very small percentage of it, that come from the moon. And we also have some meteorites that come from the Mars. Martian meteorites are very special because so far we do not have a sample return from Mars by any of the NASA missions. We are very soon going to have a very exciting mission called Mars 2020 that will hopefully in near future will bring samples back. However, so far, all we have are these Martian meteorites that are the actual samples of this red planet that we can study in the lab. So apart from meteorites, these meteorites are called the poor man's space probe because they're free materials that just fall through the sky and they are all available for us to study in the lab. But various space agencies like NASA, JAXA, etc., have actually brought material or collected extraterrestrial material that we also study in the lab. So here are some examples of those rocks. Very famous is the moon rocks from various Apollo missions. We also have material from a comet that returned the sample of a comet called Wild-2. The mission was called Stardust. We also have materials from our own sun in the form of solar wind that was implanted on these materials by the Genesis mission, which was brought back to the Earth. Apart from the missions, there are other ways of collecting extraterrestrial material as well. One of them is micrometeorites. These are distinct from terrestrial or the big macrometeorites. They're really tiny, and they actually sample the interstellar dust that's actually floating around in our solar system and not being gravitationally biased like meteorites are. And the last one is the interplanetary dust particles that are collected in the stratosphere on Earth's atmosphere. So all these samples, identifying meteorites can be a challenge. So there are certain clues that you can get by looking at a rock and decide if it's a meteorite or it's a meteorong. Most meteorites are dark on the outside, and I'm going to show you some pictures or some examples of this in next few slides. So this dark material is basically called as a fusion crust. When a rock like this enters into the Earth's atmosphere, there is a lot of friction, there's a lot of charring, which basically chars the outermost layer of this rock, forming a very dark material called fusion crust. So that's one example or one identification factor for meteorites. Some meteorites, specifically iron meteorites, have these finger poke like marks. They're called redmolips on the outside. That's another example of how you identify a meteorite. Many of the meteorites that we have are rich in metals, so they're usually heavier than terrestrial rocks. However, there are some exceptions to this rule. Not all meteorites are heavy. Some meteorites are metallic, so they're shiny inside, they're magnetic, they attract to a magnet. There are some special meteorites that are called chondritic meteorites. The name chondrites comes from these little tiny balls, stony balls, that are called chondrules, and they are very distinguishing features of these meteorites. However, rocks that are not meteorites, they are meteorongs. Some of them have bubbles or holes inside. Meteorites usually do not have any porosity in them. Some of the crystals are very distinctly visible, like quartz crystal or mica crystals, which is not a common feature in meteorites. They give colored streak if you use a streak plate and rub it against it. Meteorites do not give colored streaks. Uh, many of the meteorites are magnetic, but there are also some earth rocks that are magnetic, so that can create a little bit of a confusion. So just one distinguishing factor is not enough. You have to thoroughly study and make sure that many of the things are actually matching to see if it's a meteorite. So I'm an isotope geochemist. And cosmochemist, and I like to study meteorites by analyzing their isotopic composition. Two of my favorite instruments are shown here in the picture. I use both. The first one is called an MC IsoPMS. It's a mass spectrometer that has a really huge magnet. And what you do in order to use this instrument is you take a meteorite, you dissolve it completely in really harsh chemicals, harsh acids, and separate out all its elements by using a chromatography technique. Once elemental material is separated out and it is dissolved in a solution, you actually spray it and put it in a plasma that ionizes things. And then you analyze that in an instrument called an MCICPMS, which stands for multi-collector inductively coupled plasma mass spectrometer. The second type of instrument that I regularly use is called a SIMS or a NanoSIMS, secondary ion mass spectrometer. Now, this is different than the first instrument, where you take a slab of a meteorite, polish it really well, and then bombard it with ion beam. This ion beam will sputter out different isotopic species in it, and then you can analyze that using a mass spectrometer part of this instrument. So one of the technique is you have to dissolve everything and separate out things, whereas the other technique is you study materials in situ. So these two are my favorite instruments. All right, so here is a picture of my favorite meteorite. It's one of the most commonly used meteorite or studied meteorite called Iron. A name of a meteorite comes from a place where it has fallen. So Allende is a name of a small town in Mexico, in Chihuahua region, where this rock fell in 1969. 1969 was also a very special year. If you remember, this was the beginning of the Apollo missions. So all the labs on Earth were ready to measure all these space rocks with a really high precision. And fall of Allende was very fortunate, because this is, I think till date, this is one of the most vigorously studied meteorite that we have. So, excuse me. The name carbonaceous chondrite comes from, or the chondrite comes from these droplets. I think I mentioned them. These tiny little droplets, they are called chondrules. They're basically fiery molten blocks droplets of lava that froze in space in the very early solar system. These meteorites also have another kind of object that I study very regularly in my lab, is called CAIs, or calcium aluminum rich inclusions. These are the first form solids in our solar system. They are approximately centimeter to millimeter size. So CAIs are very special. Here is a microscopic view of CAIs, and they define time zero or age of our solar system. So here are two pictures of a CAI. The first one is actually, it's a backscattered electron image, meaning it is showing its texture, morphology, and also chemical composition. The second one also is the same CAI, but this is an X-ray map. So it basically tells you the chemical composition of this object. So as you can see, the green material is calcium, blue material is rich in aluminum, and the red material is rich in magnesium. So as you can see, this CAI is mostly green and blue. That's why the name calcium aluminum rich inclusions. Whereas the matrix of this meteorite is very red, which is rich in magnesium. This is the oldest CAI that defines the age of our solar system to be 4,567.3 million years ago. This is actually a very precise estimate of the age. So how old is it? Like, I mean, it's easy to talk about million years without really realizing what it means. So let's compare that with a person. For this person, for some reason, has maybe lost their memory or birth certificate and do not remember their date of birth. So by the same techniques, as we know the age of our solar system, it's like knowing the age of this person with the precision of plus or minus 18.4 hours. That's the time of their birth. So we know the age of our solar system very, very precisely. Biology cannot actually do that for actual human beings. You can estimate the age of a person with approximately 1 to 2 years of a precision. So we know the age of our solar system much more precisely than what we can tell about a living person. So that's why these are my really favorite objects that define the time zero where all the solar system formations started. So today I'm actually going to tell you a story about a very special meteorite fall in June, on 2nd June in 2016, when I was a graduate student in Arizona. There was a fireball that was reported by multiple people, multiple instruments like radar instruments. And here is an example of a trail that this meteorite left in the sky. I was a graduate student at Arizona State University in Tempe, Arizona, which is approximately 82 miles from here. So this is the region where this meteorite fell, and this is a Google Earth map. And what you can actually see here is the predicted path of the meteorite, and the regions that are shown here in yellow is the maximum probability where this meteorite fell. So all this is actually Indian land. This belongs to the White Mountain Apache tribe. And that's why hunting for this meteorite was not really possible or permitted for everyone. However, ASU got special permission, and we made a team of 6 people. I think I have, yes, a picture of all these. So here is me, and here is our center director at ASU, Dr. Lawrence Garvey, and a graduate student at the time with me, and 3 private meteorite collectors. And we all went on a journey to camp in this region and actually try and find this meteorite. So this is how, so the topography of this looks kind of okay, flattish, not really. So this is what the terrain actually looked like. It was full of vegetation, lots of ups and downs. So it was really challenging to actually hunt for this meteorite there. We encountered many problems. There were many inaccessible places where we probably shouldn't have gone. But ultimately we did find a meteorite. So here is an example of what we were looking at when we were looking for these meteorites. And I had not really found a meteorite before this expedition. So it was all very new for me. So this is what the terrain looked like when we were out in the field. Lots of rocks, lots of vegetation. And in this picture, we have a meteorite. In fact, we have 3 meteorites. So I am actually going to I'm going to ask you in a little bit if you can identify a meteorite in this picture. But meanwhile, once you find a meteorite, you take lots of pictures, you take like GPS coordinates for this rock where it was found for later purposes, and collect it and using gloves and all that and put it in a secure container. So let's come back to this picture. So this picture has a meteorite, or actually it has 3 meteorites. Do you guys want to guess or see where this meteorite is?
I do. Where are the meteorites? Where are the meteorites? How should people guess? Do we want to have people guess where they are, Prajkta, or do we want to have them guess how big they are? Or
That's actually a great idea. How big do you think the meteorite that you have here in this picture? Like, is it this kind of size, maybe like, or maybe that, which is like size of a strawberry, or smaller than that?
so that first rock that you were circling, that's about the size of like a baseball, or
Yeah,
yeah?
yeah, I will say that.
And the second rock that you're circling over there on the left, that's, you said, the size of a strawberry?
Yes.
Or Zara's suggesting maybe it might be quarter sized. So yeah, maybe about that size, about the size of a strawberry.
Okay.
Anyone else want to suggest how big do you think the meteorites? There's 3 meteorites in this picture. Um, Anyone want to guess about how big those might be in this picture? I'm thinking people aren't sure. I wouldn't know until you told me, so I'm guessing. Sue says that maybe it's nickel-sized. Maybe instead of being quarter-sized, maybe something about the size of a nickel.
Yeah. So
That's a good
usually,
guess.
yeah, that's a good guess. Meteorites that we find are actually pretty small. You're going to be surprised. Okay, someone says it's the upper left side, the strawberry rock that is a larger meteorite right here. Actually, that is not a meteorite. You are going to be surprised when when I show you the meteorite. Oh, about that right here.
The
Uh,
shape is interesting, but
that is an interesting shape. I think it's a bigger rock, but that is not a meteorite either. Yes, the color is a little bit weird than most of the rocks, but there is a weirder rock if you look really closely. That's here. And it's really tiny, but there are 2 more that are the fragments or the pieces of this rock. So this is exactly what we were looking at when we were hunting for this meteorite. And this is a really interesting rock. Even though it's really tiny, it came in with a lot of velocity, formed a really small impact crater here, bounced back and fragmented into 3 pieces. So these are the pieces of the same rock that we collected. And it's really tiny. So most of the meteorites that we collect, we find are actually very tiny. Uh, Here is an example of another one, which is maybe a nickel size. It shows a very beautiful fusion crust, and this rock has not been impacted hard enough to actually break into pieces. So this is intact. That's another one, really tiny pea size, maybe. And here what you see is the fusion crust has been chipped a little bit, but the rock is very distinct from what you see in the surrounding material. It's very dark. It's very obviously distinct from all the reddish rocks that we find, because this was a very fresh fall. The meteorite fell into on 2nd of July, and we were able to get onto the field with all the permissions and all within 3 weeks. So this was actually pretty exciting. So the stones have not been rained on, and they're clean and more pristine, and very quickly collected. So it preserves the fusion crust. The interior of this meteorite is actually very light. Um, Here is the biggest stone that our collection manager, Dr. Lawrence Garvey, found. This is the approximately a strawberry-sized stone. That's the biggest one. That's why he probably looks very happy. There are some things in the field that look like meteorites, but they are not meteorites. And I really found this the hard way, because this wasn't really heavy, or it was actually soft. It's actually deer poop, because there's lots of wildlife over there. So this is not a meteorite.
I can't imagine. Can you folks imagine? You're looking for meteorites and you pick up a piece of deer poop instead. Wow.
That was not the highlight of that trip.
Ew.
Here is another example of a meteorite that shows a really nice fine fusion crust, and the interior that's actually very light in color. So here is the last, like after spending 4 days in the field, we collected a bunch of meteorites, total of 16 fragments that we took back to the Arizona State University for further study. So here is the biggest rock that we found, and lots of smaller pieces. Many of them were impacted and part of the same material that we found. So many of these pieces are actually really small, really, really small. This was the fourth observed fall in Arizona, so it was kind of a special rock. This was named as, so meteorites are named after the place where they fall. So if you ever want a meteorite to be named after you, you first have to like find a village or a town and name it after yourself, and then maybe wait for a meteorite to fall there. So this meteorite, it was basically middle of nowhere, but it was close to a Indian town called Sibicu in English, or Dishchibico in the Native American term. So this meteorite is called Dishchibico starstone.
And it looks like we've got a question for just a
Oh,
second. For the older falls which lose the fusion crust, are there other telltale signs that they're meteorites if you don't see a fusion crust? Or do
well,
they lose their fusion crusts? Or
usually the fusion crust and the rock itself, when it is fresh, it will remain, it will be very distinct. But you wouldn't just lose the fusion crust, but maybe part of it. So sometimes it is intact. Many times this fusion crust undergoes weathering, or like, just like our terrestrial rocks, it will undergo weathering and disintegration. For meteorites, like there are other factors. Like for this one is an ordinary chondrite. We later did a little bit of work on it and classified it as an ordinary chondrite. Chondrites usually contain these round objects like chondrules, and in many of these meteorites, they are distinctly visible in hand specimen. So that's one of the factors that would let you decide if it's a meteorite or not. If the meteorite fall is an iron meteorite, it's heavy, it's magnetic in nature, it's not porous. So that's, or it doesn't have any cavities or vesicles and all that. So those are some signs to know if it's a meteorite. The best way to decide if it's a meteorite is actually bring it into the lab and actually analyze it chemically, isotopically, etc. But there are certain features that you can see that will tell you if it's a meteorite or not.
thank you.
All right, so most of the meteorites that we have in our collection, they come from very beginning or very early in the solar system, where there was a huge cloud, which is called a molecular cloud, and some external event, maybe like a supernova going off in the nearby neighborhood, triggered a collapse of this molecular cloud. So what you have here in this picture is an artist's depiction of what our early solar system looked like. At the center, you have the proto sun or the baby sun, because it's in the stage of formation. It has not completely formed yet. And then you have this giant disk of gas and dust. A lot of this gas and dust is at a very high temperature, where those kind of temperatures probably don't exist on Earth. It's most of the silicate material is like in the vaporized form. And as things start to condense, and all this material is actually rotating around the protostar and accreting, sticking together, forming bigger and bigger bodies. As things start to cool down, many of the rock vapor condenses to form materials like the CAIs and the contours that we find in these meteorites. And as these CIs and contours and other dust particles come together, they'll form bigger and bigger objects, which will ultimately lead into formation of planets and planetary bodies, planetesimals. So most of the meteorites come actually from very close to the sun, whereas as you go away from the central star, you start forming materials like planets, like giant planets, which are rich in gas. We know the age of our solar system at this stage because of these meteorites that contain really early form solids, which is 4,567 million years, zero point 0.3 million years, with a really high precision. After formation of things and they accrete together and they form planetesimals, many of these objects actually collide into each other and fragment, and so they are thrown onto the trajectories that intersect the Earth's trajectory. And that's how many of these meteoritical materials are brought onto the Earth. These impacts are very common. It's not just Earth, but they are observed all over in the solar system. So here are two very famous examples of planetary impacts where either larger planets bombard with each other or collide with each other, separating out these rocks, or some of these rocks actually landing on Earth, forming impact craters. So here is an example of a famous impact crater in Arizona. This is approximately 50 to 60,000 years old, near Flagstaff, and the diameter of this crater is approximately 2 kilometers. Um, there are meteorites recovered from this region. The meteorite is called Canyon Diablo, which is a iron meteorite. It's kind of famous, and hopefully we'll see some of it later. Um, Other places where planetary impacts, Earth or the terrestrial planets are not the only places where planetary impacts happen. There is an example of a very spectacular impact event on Jupiter, where planet Shoemaker-Levy impacted in 1990s and created this amazing image. I think it was observed by various places by many people on Earth. It was such an exciting, energetic event that highlighted that planetary impacts are very common in the solar system. So after one such planetary impact, this meteorite that we collected ended up on Earth. So it started its journey 4,567 million years ago, where it condensed all these little solids like corals and CAIs. It came together as a bigger planetary body and remained pristine for 4.5 billion years before its trajectory was actually, before it was impacted onto another planetary body and broken into fragments. And these fragments intersected the trajectory of Earth on 2nd June 2016, and this rock landed on Earth for us to go and collect it and then further analyze it in the labs. So this is all I have for today's presentation. If you have any questions, I'm happy to answer them. And Christine, I think, has a very exciting activity after this too.
Yes, thank you. Thank you so much, Prajkta. So folks, if you have questions, I'm sorry, Sherelle?
No, I just wanted to give Prajkta a round of applause. So that is an applause for me, a virtual applause. Great job.
Give folks a couple questions to start thinking of questions that they might like to share or ask. I'm going to take over the share to show some images here. So we have here, you might see 3 different rocks, A, B, and C, and wanted to see if you folks have questions about any of these rocks. One of these is a meteorite, but only one. Sherelle, can you go ahead and bring up the poll question here? Which one do you think is a meteorite? Do you think it's going to be A or B or C? And then we're going to give you more information, then we'll let you vote again. Somebody's typed in C. We've got some different people voting different things. Okay. Sherelle, can we go ahead and close the poll without showing them any answers or anything? And we're going to give them some more information about A, B, and C. Does anyone want to know anything specific about these rocks? Do you want to know anything about what they look like up closer? For instance, do you want to know more about how they feel or how heavy they are? We've got votes for A and for C, and somebody wants to know about how heavy they are. Well, this rock right here that I'm holding is very light compared to the other two. This one is very light, and I can see, and you can probably see here, it's got little knobs of other rock mixed in with it. Lots of little pieces of rock all stuck together is what this one kind of looks like to me, you might see, and it's very light. That's A. B is kind of heavy, although it's a thin slice that's been cut. So it's kind of heavy. I see lots of little holes in it, and I see an area here that's kind of sparkly and green. To my eyes, it's green. To the camera, it doesn't look quite so green, and it's kind of sparkly and lots of little holes in it. And C C is kind of heavy. And somebody wanted to know if they were magnetic. You know what, Prajkta, I'm going to let you talk about them a little bit while I go grab a magnet.
All right. So rock B that we see, Christine said that it is heavy, but it has lots of porosity, lots of vesicles, etc. So that's distinct from the other two rocks. This one, it looks like a conglomerate of bunch of things. So that looks a little bit weird. All right, Christine is back with her magnet.
And here I've got a magnet, and A does not appear to be magnetic in the least. B, not really. I mean, I can feel it almost, maybe just a tiny bit, but not very much. It's certainly not sticking to it, but I feel a little bit of tension, if that makes sense. It's like it kind of wants to be. Maybe C is magnetic. C is definitely magnetic. It's stuck to it. Any other questions? There's somebody has, Vanessa and Nicholas want to know more about B and what type of rock B is. Well, let's see, it's dark and it has little holes and it has these little green crystals that I'm pretty sure are olivine inclusions.
Yeah.
So Prajkta, do you want to tell them what type of rock this is?
This is probably basalt that contains inclusions of olivine, lots of vesicles. So basaltic rocks are usually lavas. That's why they have lots of vesicles. It's a lava that erupts on the earth instead of being a plutonic rock. It's a volcanic rock. So that's pretty cool. I suspect it is. Do you know where it is from?
I do not know where that particular one is from.
Okay.
You'll have to ask Alan. It's his rock.
Oh, I suspect it's like one of the San Carlos olivine.
And so Prajkta, basalts can be meteorites, yes?
Yes, actually there are many basaltic meteorites. Yes, Emily, I think it could be possibly from Arizona, the region called San Carlos, because it's very famous for the distinct green olivines that you find. I think I have it somewhere on my desk. Yes, basaltic, there are certain meteorites that are basaltic in nature. So how they form is that you form all these chondritic meteorites or similar meteorites that are similar to chondrites that accrete at the beginning of the solar system very early, so that there is enough radioactive heat to melt them. And once the melting starts and happens, all the heavy material goes into the core, forming iron meteorites, and all the lighter silicate material that remains on the crust on the mantle, which is basically basaltic in composition. So we have a bunch of basaltic chondrites. Many of the Martian meteorites are basaltic, specific ones that are called shergottites. There are many lunar basalts that we have in our collection. And from the asteroidal belt, we also have many achondritic meteorites, basaltic meteorites. Very famous example is the eucrites that come from planet Vesta.
So,
Vesta, sorry.
But meteorites usually do not have vesicles in them.
That's perfect. Yeah, that's right. Most of the degassing feature that you see in this rock is very common to terrestrial rocks, and you don't have these kind of holes in basaltic meteorites.
So, Sherelle, can we go ahead and vote again? Let's do that poll again and see what people say now after we've given them some more information. Let's reopen it. Let's relaunch the poll. Which one do you think is a meteorite now? Do you think it's A or B or C? Let me move the question off the screen so it doesn't affect your ability to see the camera there. Do you think it's A or B or C? And we're going to give you 5, 4, 3, 2, 1. And the answer is indeed C. The answer is C. As you can see, Prajkta, would you like to share a little bit more about this particular meteorite that I'm holding?
Yes, it's actually from a meteor crater that I showed you a picture earlier from Arizona. From the Arizona meteor crater called, this meteorite is called Canyon Diablo, and it's an iron meteorite. That's why it's heavy, attracting to the magnet. There are multiple pieces of this meteorite that are found around the crater. However, since it was such a giant impact, there were many people who thought that there is a larger mass of this meteorite that is buried under the crater. But actually, planetary impacts are very violent events. When a rock like that impacts onto the Earth, most of it just vaporizes. There is so much of energy in it that you don't really find materials buried inside. But many of the rocks that of the main parent meteorite are fragmented and then they fall. And that's how we have pieces of this meteorite. It also has these really interesting features called regmoliths, which are these thumb-like imprints, which are very common of iron meteorites actually. This is a feature that develops on these meteorites as it is traveling through the atmosphere.
So yeah, thumbprints. When you find a rock with thumbprints, it might be a meteorite, especially if it's dark on the outside, like it's been burned, and it's heavy and it attracts a magnet. That makes it even more likely. So we've got a couple more questions before we need to finish up here. There's a question about, please repeat the explanation, why meteorites don't have those pores, those vesicles in them again, why meteorites don't have little holes in them like some of the rocks on Earth do.
So many of the meteorites that we know, like chondritic meteorites, they do have porosity because they are just basically aggregates of dust that basically come together and then accretes and sticks together, and with more and more material being added, becomes compact. Many of them undergo thermal metamorphism, meaning that some amount of heating, not complete melting, would remove all this porosity and things would be even closer together. On terrestrial rocks, you have porosity because most of we have abundant water on Earth. So a lot of material, or there are lots of volatiles that are dissolved in the magma. As it erupts on the surface, they try to escape and create these holes or the porosity, lots of volcanic gases. You don't have this kind of phenomena happening in basaltic meteorites that you see on other asteroids. There is not enough volatiles that would escape to cause this amount of pores and vesicles and porosity in it. And that's why you don't have all the bubbles and the holes, which is a very terrestrial phenomenon that is found commonly on terrestrial rocks.
Thank you. And then one more question here about rocks being made from volcanoes, since we talked a little bit about that. There was a question about how many rocks are made from volcanoes.
Oh.
And of course, the answer depends on where you are, right? So.
Yeah. Yeah, well, there are many rocks, many types of rocks that are made from volcanoes. On Earth, we have
maybe not the different types, but would you say that a large number of the rocks here on Earth, would you say like half are from volcanic activity and igneous rocks?
Well, that's an interesting question. I think majority of terrestrial rocks are sedimentary in nature.
Sedimentary, okay.
Yes, that's my guess, though I'll have to brush up my basic geology knowledge. We do have volcanoes. We have really cool rocks from volcanoes that bring materials from deep inside so that we can analyze or understand what's going inside the Earth. But I don't think, like statistically, I think sedimentary rocks are more common than volcanic rocks.
Okay, and then when you compare that to a place like the Moon or Mars, that changes.
Yes, because you do not have all the activities like biosphere and the lithosphere that we have on Earth. So most of the rocks are formed because of either volcanic they are formed in differentiated bodies because of volcanic activity or impacts. So you have another planetary body impacting, bringing in a lot of energy, creating impact melts and breccias. That's another way of forming different kinds of meteorites, melting rocks.
Thank you, Prajkta, for your expertise and your willingness to give great detail to your questions. I want to again thank everyone for joining us. Christine, thank you for your lovely demonstration. And if anyone else wants to know about LPI, of course, you can find us on the web, lpi.edu, and we will be there in the education department to answer any of the questions that you may have. We will also be the connection if you have any more questions for our expert for this evening. We can always forward her your questions to her. And lastly, I'm going to bring up Christine to talk about our wonderful library that we have. Christine?
Absolutely. Thank you, Sherelle. Our library has been looking forward to the opportunity to provide tours and an open house at some point. But right now, the library, like the rest of us, we're all closed. So we're not actually letting people into the library in person. However, the library does have a large number of resources online, and if you would like to go and visit the collection, so go to the LPI website, lpi.usra.edu, and check out the library. They do have resources online, collections, things that you can look at. And a number of resources. They've also compiled for us for tonight a list of resources that might interest you in terms of more information about meteorites. And when they are opened, you can go and check out some of those books yourself. So when everybody's back to normal and we're in the office, swing by LPI's library and check out a book about meteorites.